Welcome everybody to the next video in our series on probability and statistics. I, as always, am Dr. Lathram, and today we'll be talking about the Poisson family of distributions. So let's begin by talking a little bit about the motivation behind the family of distributions. So the Poisson family is probably our first example of what we'll call a limiting distribution. Now that means that we'll start with an initial experiment that's pretty much the same as the binomial distribution. We have n trials with only a possibility of success or failure on a particular trial. We'll assume that we've got n trials and that the probability of success on a particular trial is given by a real number p between 0 and 1. So in our limit, we're going to actually let the number of trials go off to infinity. But something that we are going to require, even though that we let the number of trials go off to infinity, we still want the expected number of trials that we're looking at to be constant. And so remember, the expected value for a binomial distribution is just p times n. So we want that value to be constant. Now, when we say that lambda is going to be constant, what we really mean is we can actually think of lambda as being a rate of occurrence, and we can do that in the following way. Suppose that we are actually dealing with an industrial process, so we're making something, maybe on an assembly line, and we're going to watch this process being done for two different amounts of time, say capital T sub 1 and capital T sub 2. Now, our industrial process will have defects in it. So if we're watching over a longer period of time, say T sub 2, then we're going to know that, well, of course, we're going to have more errors simply because we've watched longer than we were whenever we were watching in the T sub 1 case. Just the natural reason for this, we're watching longer, so we have more opportunity to see more errors. Now, the main idea that's actually underlying this is the notion of that industrial process has a particular error rate that's going to be associated with it. And that error rate is going to be constant. So if we normalize the number of errors by the amount of time that we're watching, then that would give us a reasonable way of calling this an actual error rate. And so what we will do, if we have lambda is equal to p times n, when that's just naturally equivalent to p being our rate lambda divided by n. So we said that this was an example of a limiting distribution, so let's take the limit. So we take our PDF for our binomial distribution, which is just n choose y times p to the y and 1 minus p to the n minus y. So let's look at what happens whenever we let n head off to infinity. Well, the first thing that we will do is expand that binomial coefficient. So if we have n factorial on top, y factorial, and an n minus y factorial on the bottom, we can cancel the n minus y factorials just to give us this n times n minus 1 times n minus 2 all the way down to n minus y minus 1, and all of that over y factorial. So inside, we'll replace our p with our rate, lambda over n, and that gets replaced in both of these places. Now, as we're looking at this, the lambda to the y has absolutely no bearing on n, and neither does the y factorial. So we can pull those out to the front. Now, what we're going to do, this n to the y, and we're going to take each one of those factors and essentially put it under one of our factors that's left over from the numerator of our factorial. So we'll have n over n minus 1 over n minus 2 over n, all the way down to n minus y plus 1 over n. And then if we do a little bit algebra on the inside, those all become 1 minus 1 over n, 1 minus 2 over n, all the way down to 1 minus y plus 1 over n. So what happens to these terms that with the 1 minus 1 over n, 1 minus 2 over n, those will all go to 1 as n heads off to infinity. So what this means for the limit is the only thing that's really has kind of bearing in it is this 1 minus lambda over n to the n minus y. Okay, well again, we can separate out the 1 minus lambda over n to the n and this to the minus y power. So we'll separate those two values. But still, even for the 1 minus lambda over n to the minus y, as n heads off to infinity, this expression is also going to head over to 1. And so the only thing that's really maybe going somewhere other than 1 in our interval is this 1 minus lambda over n to the n power. Now, we recognize that as our expression for e to the x way back from our calculus days. So we've got e to the x as the limit as n goes off to infinity of 1 plus x over n to the n. And so in our limit, we simply replace this limit as n goes to infinity of 1 minus lambda over n to the n power with e to the minus lambda power. And so, of course, the natural question that we ask is, do we actually have a distribution from this? And so, things that we need to check. Well, all of the components in our function f, being e to the minus y, lambda to the y, and y factorial, all of those are going to be positive. And so that naturally means that f of y is going to be positive for all, is going to be non-negative for all y. Then we go back to Calc 1, and we go back to this series again for e to the t. Well, if we look at our summation, so now we're looking at the probability of the entire sample space. So we're summing our probabilities from 0 to infinity. The e to the minus lambda we can pull out to the outside, and what we have left is exactly the expression for e to the lambda. And so our infinite series becomes e to the lambda. We've got an e to the minus lambda. Putting those together, we end up, sure enough, with our sample space being 1. And so kind of the third axiom, as always, kind of satisfied automatically. And so sure enough, it does follow that f of y is going to be a probability density function. So what is this probability density function? This is what we mean by the Poisson family of distributions. And so we have the Poisson family of distributions, which is a family parameterized by a real number, lambda greater than 0, and the PDF defined by lambda to the y over y factorial times e to the minus lambda. This is what we will call our Poisson family of distributions. We think of that lambda, again, as being kind of an error rate or an occurrence rate for some kind of process. And we'll denote that a random variable y has a Poisson distribution with parameter lambda by y till the POI and then lambda. So quite naturally, what's the next thing that we look at is the moment generating function. So let's see if we can derive the moment generating function. So going back to the definition, the MGF for our random variable y is going to be the expected value of e to the ty. So we plug in e to the ty times our PDF, and then we can do some algebra. So the e to the minus lambda we can pull to the outside. The lambda to the y power and the e to the t, we can make those both to the y power, so we can combine those together. So we still have our y factorial in the denominator. And so again, we recognize this infinite series as just being e to whatever value is inside the power, e to that power. So we have e to the lambda e to the t times e to the minus lambda. So we can combine those, put those together, and so our moment generating function looks like e to the lambda times e to the t minus 1. So then, looking to find the mean and the variance, we suppose that y has a Poisson distribution with parameter lambda. We claim that both the expected value and the variance are equal to lambda. So let's see if that's going to be true. Well, we go back to the moment generating function that we just derived. So it's e to the lambda times e to the t minus 1. If we take the derivative, so taking the derivative with the chain rule, derivative of the outside, keep the inside the same, times the derivative of the inside, just gives us e to the lambda, e to the t minus 1, times, now the derivative of the inside, lambda e to the t. So if we evaluate that at t equal to 0, sure enough, we get an expected value for y of lambda. Now for the second derivative, we take the derivative of the first derivative, so using the product rule, and derivative of the first times the second, plus the second times the derivative of the first, and so we end up with this kind of, not a terribly complicated expression, but we'll leave it to you, the watcher, to confirm that independently on your own. Take the derivative and see if that's not what you get. We plug in t equals 0, and so we get a second moment of lambda squared plus lambda. Then for the variance, that's the second moment minus the square of the first moment, and so we get lambda squared plus lambda minus lambda squared, which again gives us lambda. So this kind of takes us through most of the ins and outs, the definitions, the moment generating function, and the mean and variance for the Poisson family of distributions. So I hope you've gotten some good information out of this, and I look forward to seeing you in the next video.